So with the integrated rate law expression for a first order reaction overall, we can use it to determine reactant concentrations after a certain amount of time. We could also use it to determine how long it takes for the concentration of something to decrease from an initial value to a final value. The other hallmark of the integrated rate law is we can actually rearrange it, we can manipulate it such that it becomes a little bit more user-friendly, especially when we have to plot data. So for example, we have our equation. So I'm going to rewrite this over here. So integrated rate law equation. So we have the natural log of A at time t over A at time 0 is equal to negative KT, right? So the way that logs work, this is the same as saying the natural log of A at time t minus, when we divide these values, and we're going to subtracting, minus the natural log of A at time 0 is equal to negative KT. If we rearrange this further, right, what we end up with is the natural log of A t is equal to negative KT, and to move this entire thing now to the other side, we end up with plus natural log A at time 0. And this is important because what it allows us to do, it allows us to make an approximation. This equation then becomes similar to the equation of a straight line, right? Which is y equals mx plus b, where the y value is the natural log of A, the concentration of A at a particular time. X there is the time. Minus k is going to be our slope. And then the y-intercept is a natural log of A at time 0, right? And this is something that we're going to be doing throughout the rest of this section, is to make or rearrange our equations so that they become easier to interpret, specifically in terms of how we can graph them. So in this example, if I were to plot natural log of A at time t on the y-axis versus time on the x-axis, what I would get is I would get a straight line where the slope is equal to the negative value of the rate constant, right? And that will look very, very similar to this plot that we have up here. So we have our natural log of A on the y-axis, right? That's your y value, x value is time, and then your graph here is going to slope downwards. So it's a negative value of the rate constant. Remember, the rate constant and the rates are always positivized. So that's where we have the negative sign. And then where it intercepts the y-axis, that's the y-intercept. That's the natural log of A at time 0, the initial natural log of the initial concentration of A. And that's important because if we have a set of data, we have a data for time, we have the concentration of A at those various times, we can plot that data. And if we see that we plot the natural log of A versus time and it gets us a straight line, that tells us that it's first order with respect to that particular reactant. So we can graphically determine the order of the reaction with respect to that particular reactant, right? And this is one of the powerful uses of the integrated rate law. Obviously, as we've seen in lab, and we talked about it, Excel or any similar, processing programs can be very helpful. We have a bunch of data and we need to plot it, we can have the program actually do that for us, and we can quickly determine whether there is that relationship. Now, remember, just as a reminder, if I was simply plotting time versus just the concentration of A, right, I actually don't see a straight line. It actually goes something like this. It's more like a curve, right? These two are not the same, right? They're not equal to each other. Here we're plotting the natural log of A versus time. Here's just the concentration of A versus time that we saw back at the beginning of this section. So that's something that we want to keep in mind.